I'm David. I'm the coordinator of the Maths Learning Centre, and this is a Maths 1B revision seminar. It's semester 2, 2017, and that's quite enough of that. So you've seen what I look like, those of you who are watching, and so you can imagine what I'm doing, but I'm not going to show myself again. All the rest of you who are here have to look at me, but you just have to deal with that. We're going to talk first about linear transformations, and then also orthogonal diagonalization, so algebra stuff. That pencil's crap. Right. So, story so far. Back in Maths 1A, or the last time you saw matrices, whenever that was, you did a lot of stuff with matrices representing linear equations, and you could use row operations to solve those equations, and you did a little bit of things with matrices multiplying by vectors to produce answers, but that was pretty much the deal. Matrices were just, rectangles with numbers in them that did various things, usually equations. Well, here we are in Maths 1B, and we're going to start thinking about matrices a little bit differently. We're going to see a matrix as a thing that acts upon a vector to produce answers. So the matrix itself is going to be thought the way we think of functions. So I'm going to start there. So you've seen functions. You've seen functions, and you've seen functions that do something like this, that take a number and produce a new number, like that. You've seen lots of those, and spending years looking at those. And you've seen functions now in Maths 1B that take two numbers and produce a single number as the answer. So you've seen things like this. And so you get two numbers and you produce a number like that. And if you've ever done any calculus, you've seen a function that takes a polynomial and produces a new polynomial. This is being a bit way out here, but you've got differentiation. So it takes like a function, I'm going to do it just on polynomials, and produces a new polynomial. So for example, it might take x squared and produce the answer 2x. So anytime you have a thing which takes some things and produces a thing coming out, it's a function. Functions do that. And so we're going to start thinking of functions, matrices as functions too, because you can now have matrix multiplication where you go f of x is a times x, where x is a vector this time. And so this takes a vector and produces afterwards a new vector. Now this might not look like a vector, but when you actually do the calculation, a times x, the answer is a vector. Any more than 2 plus 3 doesn't look like a number, but it really is just the number 5. I've just written it differently. So that's what we're going to think of here, that we're going to make functions out of matrices. And these functions take x's and produce, take vectors and produce new vectors. Excellent. So that's just one kind of function that you could do on a vector. You don't have to do them as matrix multiplication. I could do functions on vectors in any way I want, right? This function back here is already a function on a vector. It takes the vector xy and produces the number, xy plus y squared. So just some examples, I could go f of the vector xy and produce the answer, the new vector x minus y 2y if I wanted, or y squared, or anything that I want. I could do some new formula that takes the coordinates of f and produces new set of coordinates, and that would be my thing. So this one where I take the f1, 2 is 1 minus 2, 2 times 2 squared, and that's the answer, is minus 1, 8. So random things that I could do like that. Cool. And I know I can do it with matrices, right? I could go f of xy is like that. And I could create a new vector like that. Cool. I'm not getting anywhere very far. I'm talking this way at the moment because I'm trying to formulate my thoughts of what I want to say in the next hour. So just bear with me. I'm making it up as I go along here. So that's functions. And we have a feeling about how functions behave. You put things in and they spit things out. And you're used to, with number functions, representing them in a certain way. You're used to having an x-axis and a y-axis, and you line up the x with the matching y, and you create a dot there, and you draw a graph. But with vectors, I'm not going to be able to do that, because the pictures, how can I put all possible vectors on an x-axis? Because it's not a line, it's a plane. So I have to think of a new way of representing my functions as a before and after picture. Okay, so crap, I really should have done this before I wrote down the new formula I was about to do. Sorry about that. How about I just draw a picture of this first one? So what I have here is that before I had 1, 2, which is here, and it produced, after I did the function, it produced the answer minus 1, 8. Like that. And I could take, for example, 0, 0. And when I chuck it through that function, I get 0, 0 again. And every point I could figure out where it goes. And I could, if I want to, draw a shape and figure out what shape it is afterwards by following where all the points went. That's my new way of thinking about functions. Now I can actually do that with ordinary functions too. I just draw a single line to my x-axis and put a whole lot of dots on there, and a new line for my y-axis, and see where those dots go. And you can see that x squared tends to spread things out if they're big numbers, and scrunch them together if they're very small numbers. And x plus 1 just shifts everything up 1, and so we can now think about things as transformations. How do they transform what's here? Which is why we're going to talk about linear transformations. Linear transformations have the property that things that are lines before are, most of the time, lines after. They may be single points, but we'll run with that later. So this thing is going to create curves from straight lines. If I take a straight line here, then the 1, 2 becomes a 1, 8, minus 1, 8. If I put in, say, 2, 4, I get, what do I get? 2 minus 4 is minus 2, and 2 times 4 squared is 32, so it's like, ooh, up here. So this straight line is now a curve. So any shape, I can figure out what shape it becomes afterwards. This function, on the other hand, will do something else entirely. This function's interesting because it's before and after. Watch what happens. Before, I have x's and y's, and after, if I multiply this out, I'll get 3x, 2x plus 2y minus x plus 7y. I have a vector with 3 coordinates. So the before is a 2 by 2 is a 2 dimensions, and after it's 3 dimensions. It's not as easy to think about, but I can imagine changing my point here and seeing what happens to the matching point there. So if I move this along a line, it's pretty likely this will move along a line too, but in 3D. Okay, I really would like to draw the exact line that it produces, but I'm not going to be all that good. Let's just pick the x-axis, okay? So the x-axis is where y is 0. Can I fit it all on the same screen? Yes, I can. The x-axis is where y is 0. And so it looks like I'm going to get the x-axis again, but just to the 3D x-axis, but just a different shape. No, I'm not. I'm going to get something else entirely. Ooh, that's fun. Let's do that. Ignore that, because it's wrong. I want to see what happens here. F of xy came out to 3x, 2x plus 2y minus x plus 7y. So please don't take everything I'm doing here as ways to do exam questions. I'm just figuring out how the ideas fit together at the moment, okay? So if I take the x-axis, I get that, which is x times 3, 2 minus 1. How interesting is that? Because all the y's became 0. Huh. So actually, there's going to be a really bad 3D picture. This is my before. And my x-axis turned up here. So let's see, 3, 2, it's a space line down there going downwards. So it turned a line before into a line after. And the y-axis will become its own line. So a line 0, 2, 7. Like that. And I can imagine that anything that is in the middle here would produce something in the middle there. So if I tracked everything that it possibly produced, it looks like I'm going to make a plane in 3D because it's built out of these 2 lines. And this is the sort of thinking that we're going to try and get the handle on for this kind of function. Right, so that's the intro. Yay. That's the intro. And what we want to do is we want to figure out how to tell whether a function is one of these matrix ones. Okay, whether I can do it with a matrix, because matrix multiplication is way easier than all the squares and multiplying by stuff. And I'm going to try and figure out, if I do have a matrix 1, how do I figure out what this plane is going to be? If I figure out where everything goes, how do I figure out where everything goes? And I'll try and figure out some other stuff too. Okay. So in a way, we're making graphs like we used to go, this shape of function, you know, an x squared has to be a parabola, an x cubed has to be a swoosh. You know, that's what we're going to do now, but with matrix functions. Excellent. Good. And I now have an idea of what I'm planning to say. So let's see. Right. Right. Okay. So we're going to need some names for things. We're going to need to some names for things. So let's just go back to these things. So we've got 2 ideas here. We have matrix functions, And we need to know how to tell when a function is going to be a matrix just from the way it behaves. And that's where we're going to get linear transformations. So we have matrix functions and transformations, and that's how we're going to do it. So let's see. We have a definition for a linear transformation. Because mathematicians love having definitions. So a linear transformation is a function such that it goes from somewhere to somewhere. This is my before and this is my after. I don't know if your lecturer has a tendency to do M and N the other way around. It really doesn't matter. I just need letters to go in those spots. Horace Lamb has a tendency for the air conditioning to whine. So I have a function that goes from somewhere to somewhere else, and it has the property that if I add vectors beforehand, it's the same answer than if I add them after. And also, it has the property that if I multiply beforehand, it's the same as multiplying after. I have a feeling that in your course, traditionally, the F is a capital F. I use capital letters for them. There's no reason why I have to do that. It just makes it feel bigger, right? So because it's acting on vectors and not numbers, in some sense it feels like the function is a bigger function. So we were going to give it a bigger letter. There is absolutely no reason why you should use any letter you want. I mean, there's nothing stopping us using Greek letters if we felt like it. But traditions are important. It's like putting up a Christmas tree. So we're going to use capital letters. Capital letters. We have a Christmas pageant every year. We're going to use capital letters for linear transformations. So this is the definition. I can tell if something is a linear transformation if it does these things. And sure. So it may be that you have some function that doesn't look like it might be created by a matrix, but it turns out that it does anyway. So the big idea here is that we have linear transformations, which are functions that do this, and we have matrix functions that are made by matrices, and it turns out that every linear transformation can be constructed as a matrix function if we want. Now that's the big idea. We don't get to that until a little later, but the big idea is this. The big idea is that if F is a linear transformation, then f of x is the same as just doing some matrix times x. That's not the definition of what a linear transformation is. It just turns out that way. You know, well, not a coincidence, nothing is a coincidence, but a big coincidence that turns out the way it does. So there we go. That's the big idea. And we spent a lot of time trying to figure out how it's related to the matrix that it came from. So here we go. Here's an example. No. Sorry, I've already done one of these today. I'm a bit worn out, so just bear with me. Should have done you guys first. So, yeah, that's the big idea. So the big question is, how do you figure out what that matrix is? That's the big question. So let's do some, and we'll see how I might figure out what the matrix is. Make it more interesting. Okay, so I've got f. Technically there's two sets of brackets there. It's f of the vector xy, but we're a bit sloppy and we'll just leave the second set of brackets out. So f of the vector xy produces the vector 3x minus 7y in the first coordinate, 6x in the second coordinate, and y in the third coordinate. And I know because of my experience that that's a linear transformation. Just trust me for today. And I want to rewrite it as a matrix. Well, suppose it's supposed to be matrix times xy. And whatever's in this first position would have been produced by going this row times that. So let's see, I could have 3x's and minus 7y's. That would do the trick. And whatever's in this position would have been produced by doing the second row times that. So 6, 0. And whatever's in the third position would have been produced by doing the third row times that, which would be 0, 1. Yay, I wrote it as a matrix. Wasn't that fun? Okay. It's interesting. So I've been able to show that this linear transformation is writable as a matrix. Okay. That's just an example of the aim of what we're trying to do. But we don't want to do that in this situation because that's too easy. No, that's too easy. We want to find linear transformations that are really difficult, described in really difficult ways. Go, this linear transformation is the projection of these things onto this subspace, which is really difficult to describe, and we want to still figure out how to do it as a matrix anyway, because we know it's possible. That's the big idea. So that's the, yep, cool. So, here we go. Right. This thing here, this matrix, is called the standard matrix. If f of x is equal to ax, then this is called the standard matrix for f. It turns out that if you've got a fixed set of way of writing your coordinates, then there's exactly one matrix that you can do. There's only one way to write it as a matrix, and that matrix is called the standard matrix. The reason why it's not just called the matrix, because there's only one, like why give it a name like standard if there was only one, is because you may want to rewrite your vectors according to a different set of coordinates, and the new set of coordinates would have its own matrix to go with them. So every different way of writing the coordinates would have a different matrix. So we're writing coordinates in the standard way, like, well, you know, the vector 1, 3 is the vector 1, 3. So it's the standard matrix. But if we wanted to write it according to a different set coordinate axes, we would get a different matrix. That's why, that there's a name. Otherwise we would just call it the matrix. Okay, so for our purposes today, because we're going to write all vectors in the standard way, there's only one matrix. And if you can think of a matrix that works, it must be the standard matrix. So for this one, I happen to think of a matrix that works. It is the standard matrix. Okay, good. So far what have we got? We've got linear transformations, got a definition. We've got this big idea of a standard matrix. Well, okay, that's great. How are we going to decide when linear transformations are a bit crazier what the matrix is going to be? And, well, how are we going to make crazy linear transformations and know that they are linear transformations? They're the other things we're going to need to do. So in order to do that, we just want to get a better picture on what linear transformations do to stuff. Okay, we know that when we saw our linear transformation act on R2 and produce something in R3, that when it did the entire of R2, it produced a plane, which is kind of nice. You know, R2 is plane-shaped, and the object we make afterwards is plane-shaped. That was kind of cool. We want to know what happens to that. And so we need some words for what the matrix is going to do. So, or linear transformation, we know they're the same thing now, so I'm going to be a bit sloppy sometimes. However, you are going to have to use specific language. So let's see. We need some more words. So if we do this, let's collect together all the outputs. Okay? So that means that we go the set of f of x's such that x is in wherever it came from. Okay? So when I read that aloud, these are all the outputs, all the f of x's. If I collect them all together, I make an object, and that object is called the range. Okay. That's the same as what we did when we did ranges for ordinary functions. Okay, we collect together all the numbers that come out, and that's the range. Okay, so this is one thing that we can make. We can make the range. We could attempt to solve the equation f of x equals 0. It might be underlined because it could be a vector. When we did that with ordinary functions, that was finding the x-intercepts. When you solved f of x equals 0, when they were plain functions of numbers, that was the x-intercepts. So for linear transformations, it's going to feel very different to x-intercepts, but we're going to solve that. So we're going to solve that. So we're going to create the set of all the x's such that f of x comes out to 0. That's called the kernel, which I always draw wrong. I start drawing a chi. No, that's not with a K, it's K-E-R, isn't it? That's right. Is that a good notation? That's called the kernel. So I dare you in the future when you're doing ordinary functions to say the kernel of x squared minus 1 is the set minus 1, 1. When you find the solutions, the x-intercepts, start calling it the kernel, just to freak people out. Because that's what it is. If the kernel is the solutions to f of x equals 0, then the x-intercepts is the kernel. I just think that's fun. I like freaking with people. Okay. So there are two things that I might be able to make out of my linear transformation. Beautiful. And they're interesting things to me. They're more interesting than they seem because they're related to each other in rather interesting ways. Okay, so they're things that I can make from my linear transformation, and the big theorem is that both of them are subspaces. So we learned all about subspaces in Maths 1A. Well, you observed people telling you all about subspaces in Maths 1A, under the assumption that you have a feeling for what subspaces are, here's another way to make two subspaces. From a linear transformation, I can make a subspace, two subspaces, the range and the kernel. So there's some theorems. The range of f and the kernel of f are both subspaces. And why do I care that they're subspaces? Because once I know they're subspaces, I can start building them out of other vectors. I can start saying, oh, cool, if they're subspaces, they have to be things like planes and lines and that sort of thing. If they're subspaces, they have to pass through the origin. If they're subspaces, then I should be able to, given any solutions to fx equals 0, I should be able to create new ones by adding them together, because that's how subspaces work. Okay, so if they're subspaces, I can start knowing useful things about them. And if they're subspaces, they have dimensions. And once I know the dimension, I know what shape they are. Dimension 1, line. Dimension 2, plane. Okay? And actually, since they are subspaces and they have dimensions, I'm going to, just to add some more words to our lives, give names to those dimensions. Now here's where I can't remember the exact words. I think the dimension of the range is the rank. Or do these words only belong to matrices? Does someone have their notes? I may have to look that up. And the dimension of the kernel is nullity. Mathematicians are essentially lazy, right? So, you know, I don't want to say the dimension of the kernel, I'll say nullity, because that's got like one less syllable. It could make all the difference. Okay. Well, this is interesting. So let's just, I just want to think about what's happening here. You've got like a before, which is Rn, and there's an after, which is in M or whatever it is, and points here produces points here, for example. And if I collect together all of the answers, I might produce, say, a line. I don't know, it could be a plane, but anyway. And whichever answers produce 0, let's suppose this is 0 here, then I can collect all of the inputs that produce 0 and they'll make a subspace 2. Okay, so this is like the range. And I'll draw a new picture for my kernel. So maybe that the ones that all go to 0, that this one goes to 0, and this one goes to 0, and this one goes to 0. If I collect them all together, then that'll be a subspace as well. Sorry. Okay, so there's subspaces, and you'll note very carefully here that the range lives over here in the after space. It might not take up the entire after space. There's a proper word for that, but I don't think we need to know it today, but codomain. The range lives over here in the after vector space, and the kernel lives over here in the before vector space. Once you do the function on the kernel, everything just gets squashed into the origin. So it is possible that the kernel is just the origin. That may be the only point that goes over here to the origin afterwards. It may be that everything goes to the origin. Okay, it is possible for the range to be just the origin. It is possible for the range to be a line or a plane or whatever. But we do have some restrictions on how big they can be. The biggest that the range can possibly be is the size of this thing. If this is R2, the biggest the range can possibly be is a plane. If this is R3, the biggest the range can possibly be is the 3 dimensions. Okay? And the kernel, well, it can only be as big as this. Okay, that's as big as it can go. But it's even better than that. The sizes of these two things have to add up to how big this is. So the really, really, really cool theorem, which is sort of half unexpected, is that the dimension of the range plus the dimension of the kernel has to be the dimension of the space you started in. So if you have f sending Rn to Rm, then this is the dimension of Rn, which is just n, but it's important for me to think of it as the dimension of the space you start. If I write n, then I might get confused because I might sometimes call this n. So don't think of it as a specific letter, think of it as the dimension of the original space. So this is a big theorem. So that puts a whole lot of restrictions on things. If I know the range is a plane and has dimension 2, then the kernel has to have a certain dimension. If I know the kernel is a certain size, then I know the range has to have a certain dimension. And that's just wild. It's a bit like saying I found the x-intercepts and so now I know what the range is, like for an ordinary function. That's not something that works for ordinary functions, but it works for matrix functions. You know what the x-intercepts are, you know the things that go to 0. Now, then you know what how big the range is. And I think that's kind of cool. All right, so how do you find these things? This is where we get to stuff that people actually ask you in exams. Yep. Okay, if f of x, y, z is 3x minus 5y and 2z, so hint, there are ways of telling if things are linear transformations just by looking at them, and one of the quickest ways is just to write it as a matrix. Because once it's a matrix, then you know. It's 3 x's minus 5 y's and no z's, and no x's, no y's and 1 z. Okay? My before spaces are 3. Did I do that wrong? 2z. Thank you. Can't read my own writing. Yeah, there is 1z, but there's 2 of them. There's only 1z written on the page, but it's not how many z's are written on the page, it's how many numbers are attached to them. Okay, so if, just to be clear while we're at this, we do know that F sends R3 because there's 3 coordinates and produces things with 2 coordinates. Just so that we're clear on what's going on here. Okay, so let's think this through. I know that the biggest the range can possibly be is 2 dimensions, because it can't fit anything bigger in R2. And so, since the range, dimension of the range and the dimension of the kernel have to add up to the dimension I came from, the dimension I came from is 3, and the range can't be any bigger than 2. I have to have at least 1 in the kernel, because there's not enough room to fit 3 in here. So I've got, I know the dimension of the kernel plus the dimension of the range is 3, because it came from 3. And I know that this one here can't be any bigger than 2, because it's in R2. That's the biggest it can fit, which means this one has to be at least 1. The options I have are that 1 plus 2 is 3, 2 plus 1 is 3, or 3 plus 0 is 3. They're the only options I have that fit with what I've got. They all have to be whole numbers. All right, cool. I wonder which one it is. I reckon it's this one. Just from thinking about it, and you know, I wrote the question. So how are we going to tell? Well, let's see if we can just figure out what the kernel and the range actually are. So the kernel of F is a set of all the x's such that f of x is 0. So what that means is I'm solving this. That's f of x. And I want that to be 0. I'm solving that equation. So if I didn't feel like doing matrix operations, I could just get two equations and figure out what it is. This tells me that z has to be 0, and this tells me that 3x minus 5y has to be 0, whatever that is. But what most people will do is they'll write it as a matrix instead. Okay? And in fact, most people would skip this and go straight to there. So they would actually just write this. Z. And all I have to do is solve that. And I know how to solve those. I just do this. And do some row operations and get some free variables, and that will solve the equation. So I've got a pivot here and a pivot here. They're my identity matrix columns. And so I can let y be free, then x minus 5/3 of y, because of this bit here, is 0. So x is 5/3 of t, and z is 0 according to this. And so x, y, z is 5/3 of t, t 0. So the x is 5/3 of t, the y is t, and the z is 0. ta-da, I have now found every possible vector that comes out to 0 when I put it into the function. Just to check that I've done everything right, I'm just going to see if this 5/3, 1, 0 comes out to 0 when I put it through the function. So 3 times 5/3 is 5, minus 5 times 1 would be 5 minus 5, which is 0. Excellent. And 2 times 0 is, yes, it works. Okay. So, what does that tell me? It doesn't just tell me that I've found all of the solutions. It tells me that the kernel of F is the span of this vector. Because all the multiples of a vector is a span. That's how you make spans of a single vector. And it doesn't just tell me that. Since it is the span of that, and that's just one vector, I know that a basis for the kernel of F is just that vector. So don't forget that when you're asked to find a basis, what you're being asked to do is rewrite the thing as a span and then pick out the objects you use to span it. You just want to make sure they're independent. But if you solve it using free variables, they'll be guaranteed to be independent, so it'll be okay. Okay. And that doesn't tell me that. It tells me that the dimension of the kernel is in fact 1 because there's only one vector here. Well, there's more than one vector in the kernel, but I only need one vector to make a basis. Okay. Right, so now I know for sure that the range has dimension 2. It turns out that I'm really living in this land here where the kernel is 1, and so the range has to have dimension 2. Right, well the question is, how do I find the range? I know the dimension is 2. If friendly exam writer asked me, find the kernel, now tell me the dimension of the range, I would just say, well, dimension is 2 because of that dimension theorem. But if they are, so I wouldn't go to the effort of finding the range if all I needed to do was find the dimension. But just for completeness' sake, let's find the range. The range of F is all of these things. It did come from R3, didn't it? Okay, yeah. So for all the things in the place where they come from, it's all the outputs. Okay, so that's the set of all these things. So this is what f of x was. It was 3x minus 5y and 2z. And the vector x being in R3 means I can choose whatever coordinates I want. So that's what this set is. Interesting. It's not necessary for me to write this stage. But just a second, it was a matrix, wasn't it? Oh, I did it again. That's supposed to be a 2. Sorry, everybody. Easy fix, though. Doesn't change my kernel or my range. Okay. Okay, so just a second. This is all of the things I get by multiplying this matrix by a vector. And it's the same. So I'm just going to cross these out in a second to say they're not necessary. That x is going to get multiplied by this vector. And that y is going to get multiplied by this vector. And that z is going to get multiplied by this vector. And look, it's all the linear combinations of the columns. Turns out that way. You don't need to do all this working to know that. You're allowed to just know that. So we are allowed to say it's the linear combinations of the columns of the matrix. Just a cotton picking minute. That's the column space of the matrix. There's a name for the linear combinations of the columns of a matrix. It's the column space. So I don't need any of that. I'm allowed to go straight to there. I'm allowed to, I don't sort of need that. It's still true, but I don't need it. I'm allowed to go straight to here and say the range of the linear transformation is the same as the column space of the matching matrix. Now, this will only work if you know what the matrix is, of course. If you don't know what the matrix is, then it's a little harder. But it's the span of the columns. And in fact, knowing that it's the span of the columns is really cool because it's just a span. And I can find a basis for a span. In fact, I could have gotten it from back here. So, I need all the linear combinations of those columns. And the quickest way of doing that is to figure out which of them are linearly independent. And I know that because it's already in sort of Gauss, in row echelon form. Those two are independent because they've got pivots in them and the other one isn't. But if it was a little harder than that, I might have to do some row operations to tell which of them were independent. Okay, so it's the span of... which is the same as just the span of these two. Okay? I have to write it this way because in my own head that's how it works. It's the span of the columns, but we actually only need the first column and the last column to do the same span, and therefore that's the basis. Cool. Huh. Knowing that the range was 2, I could have just said that the range is just R2, right? Because that's the only thing with 2 dimensions that fits in R2 is R2 itself. I could have said that, but that wouldn't have illustrated to you how to find a range. Okay, so just a second. What have we got? So far we have that the kernel of f, so if f of x is a times x, then the kernel of f is the same as the solutions to ax equals 0. And to do that you have to do your free variable stuff. And the range of f is the column space of the matrix, which is the span of the columns of A. Well, that's useful stuff. So this is not what the definition is. Okay, the definition uses f. It's just if you happen to know the matrix, then you can figure it out from there. But I have one last thing to solve. How do you figure out what the matrix is? I mean, we've got one example where we've figured out the matrix and we just stared at it and the matrix just appeared to us. But what if your linear transformation was a bit crazier than that? How would you figure out what the matrix was? So here you go. Here's the magic of matrices. How do you find the matrix? Here we go. The magic of matrices is that when I multiply a matrix, I'll put actual numbers in there as an example. When I multiply a matrix by something here, then this tells me to do a linear combination of these columns. And so if I wanted the first column, I would say, well, I want 1 of the first column and 0 of the second column and 0 of the third column. So if I have matrix times 1, 0, 0, this should be 1 times the first column. If I have matrix times 0, 1, 0, it should be 1 times the second column. Because I'll have, if I want this second column, I can put a 1 where the y is and 0 where the x and z is, and it will give me the second column. And if I have matrix times 0, 0, 1, this should give me 1 times the third column. So that's the magic trick. I know that I can write it as matrix times vector. So if I want to figure out what the first column of the matching matrix is, all I have to do is figure out what I get when I do 1, 0, 0. So what that means is that the first column of the standard matrix for F is F of 1, 0, that vector. That'll be the first column. And the second column for the standard matrix for F is F of 0, 1, and put the 1 in the second position. And just keep going until you run out of possibilities, and that will give you all the columns. Let me redo the first one and show you how it works out. What was my matrix again? Like that. So I'm not going to do the thing where I would normally just split it up as a matrix because I'm staring at it and I can see what the matrix is. I'm going to pretend that I didn't know how to do that and just figure out what the standard matrix is using this procedure. So the first column of the standard matrix is F of 1, 0, 0, which is 3 times 1 minus 5 times 0, 2 times 0, which is 3, 0. And that's exactly what the first column should have been. And the second column is F of 0, 1, 0, which is 3 times 0 minus 5 times 1, 2 times 0, which is minus 5, 0. And the third column is F of 0, 0, 1. Which is 0, 0, 2. And so therefore my matrix is this. Therefore F of x, y, z, the first column is 3, 0, the second column is minus 5, 0, the third column is, no, just 0, 2, sorry guys. 0, 2. And that's the standard matrix there. Now that was very simple. But the idea is that if you happen to have a linear transformation that's really difficult to describe, as long as you can figure out how to find the answer for any particular for those vectors, you'll be good. Let me describe one. Of 30 degrees around the origin. So my linear transformation is rotation of the point 30 degrees around the origin. That's how I'm describing my linear transformation. I know it's linear transformation because if I rotate first and then add, it will give me the same answer as then if I add and then rotate. And if I multiply and then rotate, it gives me the same answer as rotating and then multiplying. I want to know what the standard matrix is. Well, all I need to do is know what happens to 1, 0 and 0, 1. Okay, so there's 1, 0. And there's 0, 1. We have to write them as columns in order for our linear transformation to work. They really do not look like they're the same length. Sorry, guys. and after the 1, 0 is here. That length is still 1 because it's rotated, so the length hasn't changed. Well, that's good because I can figure out that if this angle here is 30 degrees, then this height is sine 30 and this length is cos 30, and they are the coordinates of my vector. It lines up with cos 30 on the x-axis and sine 30 on degrees on the y-axis. And so that must be the first column. So f of 1, 0 became the new point, cos 30 degrees, sine 30 degrees. Just for reference, your lecturer prefers radians, probably. If you do write cos 30 as where 30 is in degrees, you must put the degree symbol. Otherwise, it's assumed to be 30 radians, which is a whole different number. Okay, and that's the first column. Let's see what happens to this one. It was there and it ended up here. All right, now this length is now cos 30 degrees because it's next to the 30. Crap, that's the y-coordinate. And the x-coordinate, which is this distance, is sine 30 degrees, only it's negative. And so therefore, f of xy is this matrix. Now, every semester people have to do rotations, and I know it's got coses and sines in it, but I can never remember where the minus is. Doesn't help that it's different spot in dynamics than it is in Maths 1B, but anyway, that's just because you're doing different things. But anyway, I can never remember where the minus is, but I know if I draw this picture that the minus is on the x coordinate of the second column, and that's how I know where the minus is. There we go. Some people just remember this, which is fine, but I can derive it, so I don't have to worry about my memory failing because I can figure it out. So what if it was a really, really fancy linear transformation, such as an orthogonal projection? Oh, really? Wow, okay. So this time f of x is orthogonal projection of x in R3 onto the plane with equation 3x minus 5y plus z equals 0. That's a really fancy linear transformation. It's very difficult to describe. It's orthogonal projection of a point onto a plane with a certain equation. How the hell am I going to find the matrix for that? Well, all I have to do is figure out how to project what happens to 1, 0, 0 and 0, 1, 0 and 0, 0, 1. That's all in inverted commas, that I need to do. If I had a really good skill at drawing in 3D, I might be able to do it from a drawing. It doesn't sound like fun, so I'm not going to do that. First, I have to figure out how to do the orthogonal projection. And orthogonal projections require me to find bases and orthonormal bases. So I'm going to have to do that first. Okay, so I'm going to need an orthonormal basis for that plane. Which means I'm going to need a basis for that plane. just a basis for the plane first. Okay, and to find a basis, I'm going to need to rewrite the object as a span. So I'm going to need to find all the vectors that satisfy that equation. So some people would write that as a matrix with one row and do row operations. I choose not to do that. I notice that this information tells me how to write the z coordinate in terms of the x coordinate and the y coordinate. Like that. Which means that if x, y, z is in the plane, then the x and y coordinates I don't know, but I can figure out the z coordinate from the other two. And I can rewrite this as x times 1, 0, minus 3, and y times 0, 1, 5. And now I have rewritten my plane as a span. So the plane is the span of those two vectors. And therefore, that's a basis for the plane. For the plane. So a basis is when your lecturer makes orthonormal bases, after they've finished making a basis, do they call the new basis V or do they call the new basis U? Do you care? I will call them U afterwards because they're unit vectors. I prefer to do what the lecturer does. Oh, okay. Freaks me out because U is a unit vector in my head, but that's okay. Okay. The reason I've done it that way is because an ordinary basis is not good enough. I need an orthonormal basis, so I'm going to have to do the Gram-Schmidt process. Yes! Just one M, right? I don't know if it's Schmidt or Smit. Is there a D? Okay. Let's put all the silent letters in. Gram-Schmidt process to find an orthonormal basis. Okay, beautiful. Okay, so you've all heard my Gram-Schmidt process song, haven't you? So it's to the tune of Fairyland Clickety Clock from the TV show The Fairies. We use the Gram-Schmidt process because we need to find an orthonormal basis, and to start we normalize, project, subtract, normalize, project, subtract, normalize, project, subtract, normalize time. Thank you. Because there's only one way to find an orthonormal basis in Fairyland, and it's to do the Gram-Schmidt process. So we need to normalize first. So we're going to find the length of U1, which is, oh, convenient. No, not convenient at all. All right, sad, but there we go. And we have to divide U by that. So my new vector is divide U by its length. Okay, so I've done the normalize. Then I'm going to have to project, subtract, normalize. Okay, so I need to project this one onto that one. And to do that, I'm going to need the dot product. Okay, so I'm going to need to do V1 dot u2 0, 0, minus 15. What sort of crap is this? All right, there we go. Okay, and so the projection is this. So we have that amount of the thing that we projected onto. Nope, yep. Which is minus 15 on 10. I suppose I could simplify that marginally. Whoa! Actually, I'm going to need to know what the actual coordinates of that vector are. 9 on 2. Okay, so I've done the project. Now subtract. So my V2, my nearly V2, it's V2 dash, is my old U2 minus the projection. So what I get 3 on 2, 1, 5 minus 9 on 2. Well, 9 on 2 is 4.5, so we just get a half. That's kind of pleasant. And now I need to normalize that. Secret, well, actually, it's a public trick. Don't do it now when there's fractions in it, because fractions are, I'm sorry, rational numbers, but fractions are less fun. No, they're more fun but take more time than whole numbers. So I don't care what this vector is, I only care what direction it is. Because I'm going to normalize it anyway, I just need the right direction. So I'm just going to multiply this by 2 so I don't have any fractions anymore. So this little sign here says equivalent to. So might as well be. Sometimes it means congruent to, which is the opposite meaning exactly the same as opposed to similar to, but that's... Okay. And now I'll normalize. So my real V, I'm going to need the length of V2 dashed. 3 squared plus 2 squared plus 1 squared, which is and of course it's root 14. Let's just make it really fun. So the V2 is run on root 14 times 3, 2, 1. So my orthonormal basis is my V1, which was 1 on root, damn it, 1 on root 10, 1 naught minus 3, and V2, 1 on root 14, 3, 2, 1. I'm not even done yet. So what have I done? I've found an orthonormal basis for this plane. Okay, and my goal was what? To find a matrix for my linear transformation, which was the orthogonal projection. Okay. So the way you do orthogonal projection is that you dot the vector with the basis and multiply those numbers by the basis. Okay, so the f of x is orthogonal projection onto the plane, which will be x dot v1 times v1 plus x dot v2 times v2. Yes. And there's all sorts of things flying around. Really? You're telling me to stop, aren't you? So David, you've talked for like 5 hours today, and you should stop. All right. So I'm nearly there. To find the matrix, I need to figure out what F does to 1, 0, 0 and 0, 1, 0 and 0, 0, 1. So F of 1, 0, 0 is 1, 0, 0 dot V1 times V1 plus 1, 0, 0 dot V2 times V2. Yes. So that number will come out later, won't it? So that dot 1 on root 10 I can deal with afterwards. 1 dot this dot that is just the number 1. Thank you. Look, I even drew this box here to tell me where the edge of the screen was, and I'm not paying attention to it at all. And this one's going to be 3. So we get a 10th there. And 3/14. Sure we do. And now we just add them together. Just. And we get, right. So I guess we'd have to times this one by 14 and this one by 10. We could probably times this one by 7 and this one by 5, and that would work too. Yes. So 7. This is what calculators are for. I can do it. And I did, see, I came down and said, when doing Maths 1B, I should bring a calculator. I'd probably done something wrong, yeah? Whatever this is the first column. I can do the middle one. Yep, do that one. And no. No, David, let's practice. I'm just going to do it over 140 if you don't mind. 14 plus 90 is 104. And 3 times 14 minus 3 times 10 would be minus 12. There you go, first column of my matrix. I just have to do that 2 more times and then I'm done. And I will just say continued. Wouldn't it be nice if you could do that in your exam? The rest is trivial. Similarly, okay. So I have a feeling that if your lecturer has asked you to do this, it would be most natural to produce a basis, like they would give you something that if you did the most natural thing, your basis would have a whole lot of zeros and ones in them. If I had thought extremely carefully, I may have been able to come up with a basis that was orthogonal to begin with if I just thought about it off the top of my head. So it's a fun game to try and come up with bases that are orthogonal. There was a classic one in an assignment at some point in the past where your plane was like and you went, well, it's a plane, it's going to have 2 basis vectors, so I just have to think of 2 basis vectors that work, right? I don't have to go through the whole process of solving it. So I could go, well, 1, 1, 0 would work. Yep, because that works. And 0, 1, 1 would work. And so there's a basis. And I Gram-Schmidt that rather than having to go through the whole process of finding a basis, because I know it's a plane, so I just have to think of 2 basis vectors, which are independent. But if I'm extremely careful, I might be able to come up with something that's orthogonal if I was paying very close attention. So, no. No, can't, no, not today. No, I really want to. I don't know, because I know that I could do this. Yes, it's not going to happen today. It's not going to happen. Okay. No. Right. That was not particularly well organised, I apologise. But thank you for bearing with me. This is the sort of thing that I used to do when, well, I wouldn't lecture to people when I was studying for Maths 1B. That would be insane. But I would help everyone with their assignments. It's not unexpected that the job I do is the job that I have, because I spent my whole undergraduate career helping everyone else with their assignments, and now that's my job. But what I would do is spend time trying to sit down and think about everything I happen to know about something, and just seeing if I can put it in any order that comes out of my head. And that's not the worst thing to do for yourself. And when you get to the end and go, oh crap, I missed this, where does that fit? And trying to fit it in. So I just crammed all the how to do orthogonal projection right at the end there as an example. And I'm pretty sure I have a whole revision seminar just on orthogonal projection. So you can go and have a look at that. But the moment, today's theme is that I can, even though the procedure of finding the orthogonal projection is way difficult, all I have to do to figure out what the matrix is sub in 1, 0, 0, and that'll tell me the first column, and 0, 1, 0, and that'll tell me the second column. So if I just remove this bit here, so far I've got the matrix is so far there's a bit more to fill in, but I just have to figure them out in the same way I did this, but with 0, 1, 0. You live in hope that your basis vectors have lots of zeros in them so that your dot products are easier to do. Yeah, rightio. That's quite enough of that, I think, unless anyone has anything else to ask about, but I'm a bit tired of linear transformations. All I would say is that don't forget that linear transformations use their own language and matrices use their own. It's just a final comment just to point out that linear transformations have kernels and ranges, and matrices have null spaces and column spaces. So linear transformations have kernels, matrices have null spaces. Linear transformations have ranges and matrices have column spaces. So if you're talking about the matrix, then you say, well, it has this column space. If you're talking about the linear transformation, then you say it has this range. It's not very important, but it's important enough for people to attach at least half a mark to. Yes?
Is it an orthogonal basis when the dot product is 0?
So the question is it an orthogonal matrix basis when the dot product is 0? Yes. It's an orthonormal basis when the dot product is 0 and all the lengths are 1. So to do orthogonal projection, despite the fact that it says orthogonal projection, you actually need to do orthonormal projection. You need an orthonormal basis, not just an orthogonal basis. So some people in their Maple TAs are caught out every semester because there's a classic question where your basis is already orthogonal, and then they get you to do orthogonal projection and you get your answer wrong. You didn't normalise them first. But if all you want is an orthogonal one, then that's fine. Just arrange for the dot products to be 0. All right. Something else. I didn't even talk about the drawing, I'm sorry. But that before and after picture is the deal. Okay. Right. I might possibly be sick of algebra at the moment, so the conics, I might wait for another day. There is quite a few things about conics on the website, but I can answer some specific questions a bit later. I thought I might try and do an overview of how the bits in the Taylor series and this infinite series fit together. So a lot of people, when they study Maths 1B, feel like you sort of get to the end of calculus in Maths 1B and you do things with derivatives and you go, sure, I can do derivatives. And then suddenly you do like all this stuff and you think back on it and go, okay, so there was like Taylor and Maclaurin and error and like infinite sums and you, in your head it's like bleh. And you feel like if you look at any one individual bit of it, you think, yeah, I could possibly do that if I remembered how that went, but I could do it. But you don't have this idea of how it fits together. And that's what I'm going to try and make up in the next 25 minutes or so. So let's see if I can do this. Right. The big idea is that you would like to represent functions as polynomials. Because polynomials are nice. I know how to do the derivatives of polynomials because I know how to differentiate x cubed and x to the 4 and x to the whatever, and I can just multiply them by the appropriate bits. And polynomials have very expected ways of having zeros, you know, and a polynomial of degree n has up to n zeros and it has up to n minus 1 turning points, and I can factorize them and I can integrate them, and they do all the nice things that I like them to do. So if I can approximate my function as polynomials, then all my calculus will be easier. And if I don't really care about doing things exactly, then I can just do approximations. Okay, that's the big idea. But, you know, most functions are definitely not polynomials. I know that. Sine of x is not a polynomial. As wiggly as it looks, and polynomials are wiggly, it's just more wiggly. Okay? Polynomials at some point will just shoot off to infinity at one end, at both ends, in one direction or the other, and sine just doesn't do that. So it might look like a polynomial in the middle, but it doesn't work at the edges. So there's just no way of getting around that things aren't polynomials. And e to the x just is not a polynomial. It doesn't come back up again on the other side. It goes up over here, but it doesn't come back up again over here, which is the way polynomials ought to behave. So things aren't, and so I have to deal with the fact that things aren't polynomials. And so I have several ways of dealing with that. So way number one of dealing, you know, that things aren't polynomials, right? But things aren't polynomials, and I have two ways of dealing with that. My first way of dealing with that is to figure out how bad my approximation is. And I go, well, what's the error? Okay, how far apart is my polynomial that I'm thinking of from the function I really wanted it to be? Or the other way around. How far apart is my function from the polynomial that I would prefer it to be? The other way of dealing with it is to say, oh, well, it's not a polynomial if I stop putting terms in, but what if I did like an infinite polynomial? Those are my two ways of dealing with the situation. I either stop and just figure out how bad the approximation is, or I go on to all the powers of x and include them all. You know, not that I can do anything infinitely long, but you know, I'm just going to theoretically imagine that I can do all of them. And those are my two ways of dealing with it. And that is why this part of the course has both error formulas and infinite series. So I want to understand how error formulas work. I want to understand how infinite series, how if I did go on forever, how would that work? How does this even work, right? What does it even mean to add to do an infinite polynomial with all the powers of x? What does that even mean? And, you know, and how do I deal with the error? And so that's why all of this is in the same part of the course. So there you go, that's my overview. Done. Yeah, maybe not. But that's the big idea behind it. So if you're ever, right, almost there. And what happens is we investigate how this even works. Is it has this upshot, is that if we know we're going to figure out how to do our best possible polynomial approximation, and if we coincidentally, and maybe not because there are no coincidences in maths, except possibly that the number of dots on a set of dominoes is the same as the number of hours in a week, this gives us a shortcut to figuring out what this is. Right. That's the really big idea. If I know enough about what I expect to happen with infinite polynomials, then if I know a few of them, I can figure out the other ones without having to do all the same process that I use to figure out the best approximation. Right. So some of the details on that. For all the details, see my collected works on the Maths Learning Centre website. I've got some details on how errors work and the different sorts of questions that you might be asked about that. I've got some details on making infinite series from other Taylor series and on intervals of convergence and stuff like that. The details on how to do some of the actual questions are around, so go and have a look for them. But let's just look a bit closer at some of these things here so we can get a better picture on how these fit together. So let's go back to my big idea. So the way the big idea works is based on two useful observations about polynomials and about functions. So observation number one is if two functions are very close to each other, then their derivatives are very close to each other as well. And their second derivatives will be very close to each other as well, if they're really close. Because you just draw the curve and well, there you go. Okay? So if I work that backwards and think, if I want a polynomial that's really close to my function, what I'm going to do is I'm going to arrange it to have the same derivative, the same value as my function at a specific spot, and the same derivative as my function at a specific spot, and the same second derivative, and so on until I get it as big as I want it to be. So I'm going to approximate f of x with a polynomial. And I'm going to arrange for f at a specific spot to be the same as the polynomial at that specific spot. And make my polynomial pass through that point. I'm going to arrange for the first derivative at that spot to be the same as the first derivative of my polynomial. I'm going to arrange for the second derivative at that spot to be the same as the second derivative of my polynomial, and so on as far as I want to go. There's going to be some point that my polynomial refuses to match my original function. Because if I differentiate a polynomial often enough, the derivative will just be 0. You know, I start with x to the 5 and I differentiate, I'll get down to something x to the 4, I'll get down to something x to the 3, something x to the 2, something x to the 1, constant, and then when I differentiate again it just disappears. So at some point my polynomial is going to run out of derivatives that I care about. They're all going to be 0. And then now I'm going to have a hope of matching the derivative of e to the x. So I'm just going to have to stop. Okay, but I'm going to arrange for these to be equal. All right, and the second observation is that when I differentiate a polynomial, something interesting happens. So my goal is to arrange for these things to match. And we notice this. If I take my polynomial, if it was like x to the 5, say, then the derivative would be 5x to the 4. And then the derivative of that would be 5 times 4x cubed. And then the derivative of that would be 5 times 4 times 3x squared. And the derivative of that would be 5 times 4 times 3 times 2x. And then the derivative of that would be 5 times 4 times 3 times 2. Because it's a constant, right? And the derivative of that would be 0. But look at this number. It's 5 times 4 times 3 times 2, or times 1, which is 5 factorial. So the nth derivative, if you differentiate x to the whatever, x to the n until it's a constant, then the constant you get is n factorial. And that is why, when you make a Taylor series, you have to adjust by n factorial. Because when you do the derivatives, the factorials just appear. So there you go. We notice that. And so in order to arrange for what we want, so my polynomial is going to have its constant term. Okay, so I'm not going to just put x in. So this thing, if I differentiate it, if I put in x equals a, then the answer comes out to f of a. And if I differentiate it, the derivative of that is just 1 and I get f dashed of a. And that's nice. And if I this x minus a is going to arrange for everything to disappear when x is equal to a. So if I differentiate this twice, I'm going to get f double dashed a, only, oh crap, because of the 2 there's going to be a 2 out the front. So I'm going to have to divide by the 2. And when I differentiate this 3 times, when I differentiate this, I'm going to get a 3 factorial out the front because that's what happens, so I'm going to have to divide by that. And I just go as far as I need to go. And this is going to arrange it to have all the derivatives match at that one spot, at the point where x is equal to a. So it's guaranteed to work there, because I set it up that way. But because all the derivatives match, it's going to work when I'm nearby as well, because all the slopes are the right slope. Okay, so that's a Taylor series. No, Taylor polynomial. Series is when it goes forever. So what we've now found is how to figure out the coefficients of the polynomial that we want. We're being creative in our interpretation of polynomial because in our head polynomial is normally just, you know, x and x squared and x cubed, but we're moving it over by a, showing x minus a and x minus a squared and x minus a cubed, so we can shift it all over to match the point that we're actually interested in. And a lot of the time we are interested in the point where it's equal to 0, because it looks simpler then, in which case the a is 0 and it's just x and whatever. So that's making the thing. So the answer to the first question is, to get our nice polynomial that approximates our function, I'm going to do this. The polynomial of degree n it approximates my function near the point A is the nth Taylor polynomial, which is this thing, which has all these things, and then the nth one is this, the nth derivative at the point A on n factorial x minus a to the n. Beautiful. Which we have. So we've figured that out. But the next thing on my list is that I need to know, but it's not equal to this polynomial. It's not ever equal to this polynomial. It's e to the x is never equal to a polynomial. And so I need to figure out how bad that is, which is what the error formula is all about. So imagine that you live in a land where you can't figure out the exact answer for anything that isn't a polynomial. You can theoretically talk about e to the power of x, but you can't calculate exactly what e to the power of x is. Imagine you live in that land. In fact, you do live in that land, but since we can do it to like 15 or 20 decimal places, you don't care. Okay? Your calculator is programmed to be able to figure out the approximation to e to the power of x to, a couple of decimal places beyond what it shows you on the screen. But imagine you lived in a land where you didn't know even up to like the third decimal place. How would you figure out how bad your polynomial was if you didn't know what the real answer was? That's the idea behind that error formula with the z in it. I mean, if you knew what the real answer was, you'd just subtract it from the approximation and that would tell you how bad the error was. But if you couldn't find the real function itself and all you had was the approximation, how bad could it be? And that's what the error formula is. Just to colour code this, that's the bit we did first. And that was what we were doing here. A big idea. And now we're doing this bit. Just in case the colour helps you, it certainly helps me. Of course, if I were doing this at home, I would probably get a great big piece of paper and just write everything under the titles that I had. Okay, so the error is, how bad is approximation is it? And what Taylor did, which is extremely clever and is a very fabulous use of probably the mean value theorem, but at the very least the intermediate value theorem, very cleverly figured out a way to figure out how bad the error is. Not exactly, but at all, An answer is better than none. A non-exact answer is better than no answer. So he says that if the real function is the polynomial and a bit, then he said that if I know what x is, and I know what n is, and I know what a is, I can get an approximation from the error. The actual and a bit is do exactly the same thing as I would do if I was doing one of my Taylor polynomials. This is his clever thing. He said, okay, so this would be the next term in my Taylor polynomial. And it's totally not going to be the and a bit, because if it was equal to this with an a, it would just be the next bit of a polynomial, and my function isn't a polynomial, so it's not going to be, it's still going to not be a polynomial. But what he said was, well, sure, this comes out to whatever answer it does when I put an a in this spot, but what would it come out to if I put a different number in that spot? Maybe if I put the right number in this spot, it would come out to the correct answer for the error. And what he figured out was that, yes, actually, if I do put a different number in that spot, it is possible, In fact, it's guaranteed that there is a number that can go in this spot to figure out the correct error. Sadly, we don't know exactly what that number is, but at least he narrowed it down for us. For some choice of z between the x and the a. Now each x, I'm going to have to choose a different z, sadly. And none of them I know exactly what the right z is, even more sadly. But at least I can narrow down the choices for what z could be. And so what I do is I go, all right, well, I know that if I put in all the numbers between x and a, one of them is the correct answer for the error. So out of all of those possibilities, so if you sub in all z's between x and a, one of them gives the correct Rnx. I don't know which one, it could be two of them, who knows. And so what I'll do is these are all the z's that I could pick, and here's my a and here's my x. And these are all the things that the error comes out to when I use those formulas. Possible answers for my error formula. Well, it can't be any worse than this one. That's the biggest one. Can't be any worse than that, the error. I mean, it could be, you know, as good as this, but I don't know which one it is, so that's the worst one. So what I'll do is I'll pick and it's got to be better than that. And that is why we care so much about the absolute value of the error, because we just want to care about how far away it is as opposed to the actual answer. Technically, this gives you both whether it's above or below if you pick the right z, but it's just too hard because we don't know what the right z is. So all we have to do is figure out which of the options for z when I sub it into there gives me the biggest possible answer, and the error's got to be better than that. So this thing here, this is my max. And so therefore, the Rnx must be less than or equal to whatever that max is. So, you know, if your Rn, if this formula turned out to be some wicked multiple of sine x, then you'd go, oh, well, the biggest answer is 1, so I'll just say it's got to be less than 1. That's just bad, the idea behind it. And you've got to also realise that this x here is a specific x that I thought of earlier. When I'm looking at this formula, it's a particular x, not all the x's, just my x right now. But the z's are, we don't know which ones they are. All right, well, that's the best we've got. But it does allow us to at least say, all right, well, it might take us a while, but I do know at the very least that it will tend to be better the closer I am to a, because this bit will be a really tiny number. You know, if x between x and a is 0.001, if I raise that to the power of 15, it's lots of zeros, 1, and that's going to be small enough to, you know, deal with any of that crap and make it really tiny. So the closer I am to x, the better it's going to be. All right, so that's my way of dealing with the error. You can look at the other videos to look at some examples of how to deal with that. So then the other solution is not to say, well, how bad could my answer be, but to say, well, reasonably, if I stop at any point, there's some error, so why don't I go forever and then it'll be equal? Yeah? Because it's just like if I want to get from here to the door, I have to go halfway, and then I have to go halfway, and then I have to go halfway, and then I'm never going to get there. Unless I go forever, and then I can escape. Right? So, right? And mathematicians are, if nothing else, are fascinated by forever. way back from when you learned that you know, a third was 0.333333 forever. We're just doing more of that. Okay, so new colour. Let's go orange. Okay, so now I want to go on forever, which means I need to know what it means to go on forever. And if I pick any specific x and sub it in, I'm going to get something that goes on forever, right? It goes on forever. So I need to know ways of dealing with going on forever. Now I know some of them already. I know this. So I know that if I go 3 tenths plus 3 hundredths plus 3 thousandths plus 3 forever, I get a third, because that's just 0.333333. I know this. This is good stuff. I'm going to base it all on that, sort of. Okay? And I did my thing there. I know that if I go halfway, and then a quarter of the way, and then half of that, and then half of that, I'm going to get all the way. These I know. Maybe I don't have any particularly rigorous mathematical proofs for them at the moment, but I feel good about them. So, okay, that reasoning is what it's all going to be based on. It's just that the idea that the difference between where I'm up to, what the sum is so far, and where I'm headed for gets smaller and smaller and smaller. Okay. So now I'm going to start thinking, what sort of random infinite sums could I do? And when could I tell if they are, if they have an answer or not? So, infinite sums can I do? When do they have an answer? If I have a different infinite sum for each x, which x's make it work? All of these things. If I have a different sum for each x, do I have a formula based on x that tells me what the answer is? And even better, can it tell me what those Taylor polynomials were? It's a big hope. You know, it would be really nice if it did match up with the Taylor polynomials. And the answer is yes, it does. Yay. Okay, so I've got all these questions and I need to answer those questions. And that's what the questions that this section on infinite series is about. Which things do I know? We need a word for this, for working, and we call it converging. So if we need some notation and we need some words so that we can talk about it. So this AN represents what these numbers are for different values. And this is n equals 0, n equals 1, n equals 2, or whatever. So I start to have ways of having notation for it. And I have terminology where I go, well, if it's actually equal to a number, then we say it converges. Just like I am converging on the door when I'm attempting to escape by going halfway at a time, same deal. And we just have to we investigate these things so that when we go back and try and do our our infinite polynomials instead of stopping when we do our Taylor series, we can be sure about what that might even mean. And that's why we talk about those things. And so it turns out that there's all these ways of attempting to tell if things converge or not. And you've got a list of them, which I won't go into the details here, but you've got things like, you know, we want converges and we want to know when does it converge. When does it converge? Well, then we've got all these convergence tests, like the alternating series tests. and the ratio test, right? And if you do real analysis 2 in second year, you'll learn like a list of other tests, like the integral test and the comparison test and the, can't remember most of the others. Okay, when does it converge? You also look at just some of the nice ones that you happen to know the answer to, you know, some classics like sum from 1 n equals of 1 on n, you know, some classics, and you go, it doesn't converge because someone convinced me, can't remember the exact proof, but I'm convinced that that one doesn't converge. So, okay, that's good. And then we want to know, well, if I have a different one for every x, when does that converge? I don't really care about having whatever I want for any x. I really care about the ones that are basically polynomials, because that's what I'm interested in, doing polynomials forever. So if it's like something times x to the n, when does it converge? Because that's my polynomial, right? My infinite polynomial. Well, that's the whole point of the radius of convergence. It tells me when that converges, depending on the value of x. There's crap in here, but, you know. That's what the radius of convergence answers the question. When does it converge? So I find a useful way of organising this part of the course is to say, what question does each of these bits answer? Okay? And then the magic happens. It turns out that if you do go with your Taylor series forever, you do get exactly equal to e to the x in the context of what we mean by forever. And it turns out that there's only one way to do it. Just like my linear transformations only had one matrix. Well, if I want my Taylor, if I want an infinite series that has x to the n's, and I want to write my e to the x as one of those, there's only one way to do it. So if you think of a way that works, it must be the way. And even better, if you think of a way that works, and then chop it off so it doesn't go forever, it's guaranteed to be the matching Taylor series without having to do the derivatives. So I need to show you this example to show you what I mean. So this is when I get to this shortcut here. Shortcut. Here we go. Here's my shortcut. So, yep. So the shortcut is based on two things. If some function is equal to a0 plus a1x plus a1 2x squared plus blah, 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 then there is only one choice for the a's. And even better, and chopping off the beginning of it will give you a Taylor polynomial. Pnx for f of x is found by chopping off at x to the n. So I don't need to do all my derivatives anymore. Crap, sorry. It's found by chopping off at x to the n. So I don't need to do my derivatives anymore, because sometimes they're really awful. All right. So I want to do an example that's really spectacular, but I might not be able to think of one. So, oh, and this applies even with the x minus a's and whatever as well. Okay, so what if I wanted to find like the third Taylor polynomial let's do a Maclaurin because that's easier. So Taylor, I could say Taylor polynomial at x equals 0, or I could just say Maclaurin polynomial, and that's the same thing. X squared e to the x. Yeah? Nice. Okay. Here we go. Well, e to the x is 1 plus x on 2 plus x cubed on 3 factorial plus x to the 4 on 4 factorial forever. That's its infinite series that is equal to e to the x. I know this, well, because it's a Maclaurin series. So when it goes on forever, you call it a series as opposed to a polynomial. This is something I know because we figured it out earlier. Here's one I prepared earlier. So x squared e to the x will be just times everything by x squared. Right? Sweet. So if I want the third Taylor polynomial, like the third Maclaurin polynomial, I'll chop it off here at x cubed. Ta-da! That's it. Isn't that fun? Way more fun than finding the second and third derivative of x squared e to the x. There you go. Of course, this won't tell me what the error is. To do that, I'd have to do my derivatives anyway, so less fun than I hoped. But all the same, it won't tell me the error, which is really sad because the error is based directly on the derivatives. But if I'm happy to just run with my third Taylor polynomial and believe that I'll be okay, I'll be happy with that. And the fourth one is this. Yeah. And this is just fun. And the people in Engineering Maths 2B have been doing this like this week. And they've had things like, so find the Taylor polynomial for e to the x at x equals 3, right? So it should have all these x minus 3 to the power of whatevers. This is the a we're referring to. So when you say at, this is the a. So you could go, all right, well, e to the x is this. I could write it as an infinite sum if I desired. All right, I need there to be an x minus 3, right? Like that. E to the x is the same as e to the x minus 3 plus 3. That's e to the 3 times e to the x minus 3. And e to the x minus 3 is what I get when I sub in x minus 3 into that formula. So that's e to the 3 times yay, done. That's it. It's done. because it's a thing with x minus 3 to the n's in it. So I don't know, that gives me a sense of pleasure that probably is a little more than it is reasonable, but anyway. It's the end of Maths 1B. We've got to take our joy where we find it. All the same, that's for the past few years, this part of the course hasn't been emphasised. It is technically there. You can have a look at it. But that's one of the reasons why you would go down this path of going on forever, because it shortcuts back to figuring out some of the things without having to do the derivatives. There we go. Good luck.